All right, so we're continuing section 2.7 on the inequalities. And in number 2, the problem was actually given in the form that I like it in. I like to have 0 on one side, and this one's already there. So looking at the 4 terms, my first thought might be, again, to factor by grouping. If I pull out an x squared, I would get x plus 2. And the only thing I could factor out over here would be a negative 1. That leaves me 2x plus 1. That's not going to work. I don't have a match, and therefore this is not factorable by grouping. So when I go to solve my related equation, I'm going to need to use another technique. Let's go ahead and write the related equation down. Like so. And since I couldn't factor, the rational zeros theorem is usually the next thing that I would try to see if I could figure out solutions to that equation. So I'm going to say, if there are rational zeros, p over q, p has to be a factor of 1. So plus or minus 1 are the only options there. And q also has to be a factor of 1. So plus or minus 1 are the only options there. That means 1 over 1 is 1, or if I use the negative on one of them, would be negative 1. My only candidates for rational zeros are 1 and negative 1. Let's go ahead and graph, excuse me, not graph, but I'm going to put the equation in here, just so I can use my table. 1 and negative 1. So it looks like 1 is a 0, negative 1 is not. So, knowing that 1 is a 0, let's divide the x minus 1, the factor x minus 1, out and see what we're left with. I haven't done a long division for a little bit, so let's go ahead and do this one by long division. X minus 1 is what would have given us the solution x equals 1. And we're going to divide that in to our original polynomial. X cubed divided by x is x squared. And when I multiply, x to the third minus x squared. Subtract makes that negative and that positive, leaving me 3x squared. And I'll bring down the rest. 3x squared divided by x is positive 3x. And again, I multiply. 3x squared minus 3x. Subtracting makes that a negative and that a positive, leaving me x. Bring down the minus 1. And x divided by x is 1. Multiplying gives me x minus 1. And subtracting leaves me a 0 remainder. So at this stage, I need to figure out when x squared plus 3x plus 1 would equal 0. And that I can do with a quadratic formula. Negative 3 plus or minus the square root of 3 squared minus 4 times 1 times 1 over 2 times 1. And let's see, 9 minus 4, that would be the square root of 5 over 2. So there are the other in addition to the 1, there are the other zeros of the polynomial. We will have to test those 3 zeros on our number line. So let's do that. Now I'm going to go ahead and get decimal values for these so we know about what numbers we need to choose when we plug in. So let's see, -3 plus the square root of 5 over 2 is about -0.382. And if I use the minus, I get about -2.618. So let's see. -2.618, -0.382, and then the 1 that we found from the rational zeros theorem become our values on the number line. And I'm just going to pick out some test points here. Let's do -3. In between there, maybe -1. And in between here, maybe 0. And then I'll do a 2 out here at the end. All right, just a quick reminder, we are looking for values greater than 0. So let's turn to the calculator table. I already have my function in here. My first test point is -3. -4 is not greater than 0, so this one's false. Next, -1 happened to already be in there. I got 2. 2 is greater than 0. True. 0. 0 gives me -1. Not greater than 0, that's false. And then finally 2. 11 is greater than 0, so that last one is true. So, let's see. We wanted strictly greater than 0 this time. Not equal to, so I'm going to use parentheses everywhere. From, and if I wanted to go back to my exact values, I could go back and say this one actually came from -3 minus the square root of 5 over 2 to this value, which was really -3 plus the square root of 5 over 2. And then it's true again from 1 to infinity. So I was picking out this section here, and then this section here. Of course, if you don't need exact values, you can always use the decimal approximations, depending on what your goal is. All right, one last example. Oh, and I'm sorry, before I leave this one, let me come back here one more time. Since we've already got this in the calculator, I didn't check the last one with technology. Let's just take a quick look at the technology solution to this one. We've already got the graph in the y equals. So I'm going to go ahead and say, it looks to me like things are fairly small. Let's set a window. -5 to 5 should be plenty on the x. I've got a -10 to 10 on the y. I'm going to just try that. And it looks pretty good. The graph is greater than 0, right? Positive. Up here, that corresponds to from -2.6 to about -0.4. That makes sense. And then it's positive again out here at the end from an x equals 1 and then forever after out to positive infinity. So our graph does seem to correspond well with what we found. All right, one last example for this section. let's see, this one is not in the form I like it to be in. I don't have 0 on one side. So let me both multiply it out, 2x to the 4th plus x squared, and also bring the 15 over. Minus 15 is less than 0. My related equation would then be 2x to the 4th minus x squared minus 15 equals 0. Since there are 3 terms, I'm going to try product and sum for factoring. Looks like quadratic form here to me. So we need a sum of negative 1 and a product of negative 30. I think it's going to work this time. If we went with 5 and 6, put the negative on the 6, that would add up to negative 1. So let's factor this. 2x to the 4th. I'll split up my middle term. Plus 5x squared minus 6x squared minus 15 equals 0. And then we'll factor by grouping. Factoring out an x squared gives me 2x squared plus 5. And I'm going to factor out a negative 3, which also gives me 2x squared plus 5. 2x squared plus 5 is my common binomial. And then I've got x squared minus 3. If 2x squared plus 5 is equal to 0, then x squared would equal negative 5 halves. And you can probably already see we're going to get imaginary solutions on this one when we take the square root of the negative 5 halves. With inequalities, we don't worry about the imaginary solutions because they're not on the number line. The second factor, if x squared minus 3 is equal to 0, then x squared equals 3, and x would be plus or minus the square root of 3. So I do get a couple of values to put on my number line. We'll test. Negative square root 3 and positive square root 3. Square root of 3 is approximately 1.732. So that's about negative 1.732. Negative and positive. All right. Let's see. I'm going to test negative 2, 0 in between them, and positive 2. So in my calculator, I'm going to go back and put my original polynomial, 2x to the 4th plus x squared minus 15. And in my table, I'll do my test values. I want these, by the way, to be less than 0. So in my table, if I try negative 2, I get 21. That is not less than 0. So we're false here. 0 gave me negative 15. That is less than 0, so this is true. And then positive 2 gave me 21 again, not less than 0. So that one is false. My answer to this then is just that one little interval going from the negative square root of 3 to the positive square root of 3. I am using parentheses rather than brackets since it was just less than 0, not less than or equal to 0. All right, that wraps up this section.